So here I am going to give just an overview of what I could find in the literature and in databases for models for GABA-A receptor subunits. If I am missing anything, please do let me know. This was just what I and one of the interns at Combined Brain were able to find. But yeah, if I missed a mouse model of yours, that was not an intentional oversight, please do let me know. So yeah, I'll go through the animal models, in vitro models, and patient samples that we have. And rather than discussing phenotypes about them, I'm really just trying to show what it is that we have so that we can get an idea of, what is currently existing and what might be needed for future development. So we can see that for some subunits, we have a lot of models, while other subunits, there really isn't much. So for alpha-1, there are a number of different mice, including a conditional knockout, and there's a zebrafish model. Most of what I found was mice, but every once in a while there was a zebrafish. Alpha-2 got, again, a knockout and conditional knockout, and a handful of mutants. Alpha-3, there was not very much. These knockouts were two different knockouts. They were created in different ways. Alpha-4, I couldn't find anything that had looked at patient variants. There was only the knockouts and conditional knockout. Alpha-5, there was the knockout and conditional and one variant. And I believe that variant was not a patient-derived one. It was more for studying just the drug receptor properties of that. Alpha-6, not very much. Then for beta-1, I actually was not able to find any models at all. So this seems to be a gap that we have where it might be of worth to develop a beta-1 mouse model so that we can understand more about that phenotype. Beta-2, not much. Beta-3, there was a few more, multiple people studying the knockout, and I found that there was the conditional knockout was also being used by a number of labs. Then Caddy and Steve Moss have a different patient-derived mice. Gamma-1, again, I couldn't find anything, but if you know of one, please do let me know. Gamma-2, there are a whole bunch. Gamma-3, there's just the knockout that was created by Jackson Labs, but then, to the best of my knowledge, is not really being utilized. Delta, there's a little bit. The Epsilon subunit has been created by one of those companies that just makes a bunch of mice, but no one is using it, to the best of my knowledge. And then Rho subunits, there is a little bit of research being done. And not a whole lot that's being used. So these mice seem like they exist. So there is not the hurdle of paying for the development of the mice. Like they exist, so you would just need to get them and start doing your experiments. Then Pi subunit, I, again, was not able to find anything. Same with Theta. Then for patient samples, because this is a new foundation, we do not currently have a whole lot yet, but the foundation is very motivated to get more samples, and there are arrangements through Combined Brain with the Van Andel Institute to be hosting all of these samples. So in 2024, they are going to be pushing to get from all of the different genes, multiple variants from each, and a lot of different patients' sample types. And then when we collect PBMCs, then those can be de-differentiated into iPSCs. So for the next 10 or 15 minutes, let's try to talk about what additional models might be needed, whether it's different types of mice, perhaps humanized genes, or if there's any use for other animal models, like more zebrafish or fruit flies or something. Are there any particular variants that do not yet have in vivo models and we need that? And for patient samples, is there anything in particular that researchers feel that we need?
I can speak to a little bit of my bias, but conditional mice and mice with variable on and off variants, a TED-O system or something along those lines, would enable us to ask questions about the compensatory changes and whether or not those are normalized and at what stage. And you could also ask questions about rate of restoration in a gene therapy and whether or not a rate that's too fast might be dangerous or a rate that's too slow might be ineffective, and age at which these things are relevant or not relevant to unwind any compensatory change. I think the tech to make those is widely available. I think that they, if they were available, will be used by a handful of labs, and they have an almost immediate translational relevance.
I'm just going to jump in, there's an orphan disease group at Jackson Laboratories, and they're amazing to work with. I've done a lot of collaborative projects with them, like SLC6A1, they're making that conditional mouse. And if you go to them, a lot of times they'll do it for free. Like if you can say that there's a need, if you can say that there's people that definitely want this mouse that will work on it, or you can say there's a therapeutic strategy we're pursuing, we need this mouse to test it. If you kind of go to them with a plan, explain why it's needed, then very often they'll just make it for free, and they'll make it available to everybody, and then it's in their repository forever. So they're a really good resource if we identify anything that's like on our hard wish list to go to them with.
So what's the name again?
It's just the Orphan Disease Center at Jackson Laboratories. Kat Lutz runs it, Lutz.
Steve, since you're here, if we consider gene therapy, at the Fandia, we already have a working mouse model in alpha line, beta space, and necrotic. So what those, So those are identified in de novo patients. We know that some maybe have a dominant-negative effect, but in mouse model, we've already characterized they have a pretty good phenotype and correlate with what I have identified in human patients. So this could be a good resource if you want to pursue gene therapy quickly.
Well, yeah, the translational discussion is probably a little bit later.
Yeah.
And also the two that there weren't any models, that's something else you could go to them and say, there are no models. And
Mike is still good, so I think we could maybe.
everybody can probably hear me out.
Yeah, just for anyone else.
Yeah, so with those you can say, there's no mouse model at all.
Yeah.
And then they'll probably be willing to try to make, and there's probably a reason, they're probably hard to make for some reason, but they can get they're the best people in the world at making these mice.
So an interesting question might be, if they have a fixed bandwidth for making the mice, how do you prioritize the subtypes? Where do you start?
Yeah. I mean, they have a pretty wide bandwidth, but it's, yeah.
But also they do have a long delay, and it still takes a while to make a mouse, especially for any of the conditional and inducible models. Then still maybe they could be making them all in parallel, but I don't know if the funding would allow for that. So there is still perhaps some prioritization that needs to happen.
And it's not an easy game. We call it the Goldilocks mouse because the variant goes in and it doesn't have a phenotype. It's not any use to you, or for the big part, at least in the beta scenario, we collectively made 5 or 6. Only one's got through. So, and that wasn't me that made this strategy, it was more Philip, but it was basically a variant based on the human that was middle ground, not really bad, not really weak. But you're rolling the dice that very often these mice don't survive or do survive and don't have a good phenotype.
This is hearsay, but I can say that there is a large pharma company that is developing GABA-A receptor variant mouse models, and they've said that the biggest hurdle in modeling this is that a lot of the mice have no phenotype. Like they knocked out 3 different receptors, in one of their model, and they like could barely find an electrophysiological signature.
It was all three.
All three of them were not
Wow.
yeah
Individually or all together?
all together. So yeah, you're gonna run into a lot of things that haven't been published too.
Yeah. The other question is some variant maybe you get mouse, but it's not available. What is available for a while, but cannot produce. So that's why we had a collaboration with the Japan group T2079M now. The mouse, only one animal survived until 8 months old, but the mouse have so many seizures, constantly jumping around, and basically lost. Not only one. Down. So spend $30,000. But we know that.
So there's
Not-
some cool techniques that I've learned through other disorders. Where, yeah. So from looking into other disorders where the variants cause very severe phenotypes and the mice are not viable and there are difficulties maintaining a colony, people have gotten creative and have some like alternate exons. It only works for the last exon of a gene, but for any of the variants there, it can, I'm forgetting how exactly it works, but it basically are able to kind of circumvent the viability problems. And I think it's like you cross with a Cree that's like ubiquitously expressed in development, so that you don't need to have a like breeding pair that has the mutation itself. It's only the offspring, and you maintain the colony that way. So for any of those viability problems, people have gotten creative, and so there are perhaps solutions if we feel like we really need some of those mice.
Yeah.
Conditional mice are a very smart way to go, but they're expensive to make, or more expensive to make, and do have their big challenges. They're not easy to make.
We recently lost 2 beta-3 locking because, we basically lost 2 beta-3 locking because I have a very difficult time to breed. You cannot, because when you do behavior test, they will have like an autistic phenotype, you want a magical or animal, but you just cannot make a mouse breeding, get animal pups at the same time. So we'll end up put them down. Yeah.
Yeah, there's a situation in this field that probably we ought to put onto the table because it may be instructive in regard to the use of animal models. So there was an interest in trying to determine which subunits, alpha subunits, were responsible for either the sedative or the anxiolytic activity of benzodiazepines, with the idea, could we dial down the sedative effect and just have an anti-anxiety effect? And it was also found that there was a single amino acid substitution that could be made in the subunits that would prevent binding of benzodiazepines. So they did this, and they came to the conclusion, based on a very extensive series of studies in mouse models, that the alpha-1 subunit is responsible for sedation, and alpha-2 and alpha-3 are the anxiolytic GABA-A receptor subunits. So that caused companies across the globe to try to screen molecules and determine molecules that are alpha-2, alpha-3 selective, right? And they had great success, actually. And there are a number of molecules that were developed that did this. And when they took them into humans, it turned out that they didn't have lack of sedative effect. They weren't that different from ordinary benzodiazepines. So this is kind of the problem with this field, that you might not have this translatability. Now, these molecules are actually getting repurposed. And there are a number of companies that are now taking these molecules and saying, hey, they didn't work for anxiety, maybe we can repurpose them for epilepsy. And that was kind of a heretical notion, because we thought, based on the mouse models, that it was the alpha-1 that was predominantly responsible for the anti-seizure effect. And here you're dialing it out. But subsequent work has shown that alpha-2 and alpha-3 selective drugs can also have anti-seizure effects. So they're in clinical trials right now. We'll find out whether they're effective. And they're not thinking about them in terms of targeted therapies for any GABA-A receptor variants that I'm aware of. They're developing these drugs for focal onset seizures writ large. So maybe we could think about situations where these drugs might be effective, and they could be potentially targeted therapies.
I want to add on because Roche, Maria just left, they have so many hundreds of compounds. We can take advantage of that. Also, as Dr. Rogaski's mentioned, GABA-A receptor has been a major target for anti-seizure drug development. So we have an advantage, as you said. So I have a huge advantage here.
We're going to move along to more of a just general translational. If you have any notes about models, feel free to email me or continue the discussion afterwards.